Hey everyone, welcome back to Calculus 3. This will be lecture 24. This will also be the final lecture of this class. In this section, we're going to introduce the idea of the triple integral and take a look at some of the applications. And a particular application that we'll be looking at is just finding volume with the triple integral. So let's go ahead and jump into it. And we'll call this section 4.5, triple integrals. And what we want to kind of start with is, as per usual when we introduce a new kind of integral, we want to start with some kind of a construction that justifies the integral's usage, and justifies the existence of the integral. Like, what do we mean by this thing? How does it work? That kind of a. And so the procedure that we'll use to define the triple integral is going to follow the procedure used for double integrals in the main. Okay, and so to do this, to kind of set this up, we need to consider a function f of three variables. All right, obviously x, y, z. And f needs to be continuous. That is continuous on a bounded solid region Q. We'll just name the region Q. Nothing meant by the usage of the term of the variable Q there, except that it's just arbitrarily chosen. Okay, and so we're going to draw this thing out here in a second. Right, so in the usual way, you can imagine, maybe I've got some kind of a solid figure here in three-dimensional space. Okay. Now, what we're going to do is we're going to encompass, so this is our region. This is the region Q. All right, it's this solid region. So what we're going to do is we're going to encompass Q with a network of boxes. Okay, we're going to encompass Q with a network of boxes, and we're going to form an inner partition of Q that's going to basically consist of all the boxes lying entirely within Q, right? So let's start by just kind of drawing what we mean by this. So I'm going to redraw this over here, but I'm going to start by drawing the grid first, just because it's much easier to do if you start with the grid. Okay, and this is going to be obviously a very crude grid. This is going to look like basically cubes, right? So it's going to look like this. And it doesn't matter if it's drawn perfectly, obviously. We just need to be able to see the idea here. Okay, now let's just say this thing resides in our XYZ coordinate system here. Right, so you can imagine these all kind of come together here at the back. Okay, so this is our three-dimensional grid. Now inside this grid is the shape that we're interested in, right? So inside there you've got your shape, but it's all gridded off into these rectangles. Okay, and so you can see obviously these cubes will completely envelop they'll completely encompass the region Q, the solid region Q. Okay, so that's what we start with. And if you imagine the shape here, Q, that's in the region, there's going to be some subset of these cubes that we've drawn out, which are going to lie entirely within the region Q. So some subset of these cubes will lie entirely within the region Q. Okay, and what we want to do is we want to use that subset that falls within the region as our approximation to the volume of the solid region Q. Okay, so if we consider a single box, right, let's just take this one for example. Right, you can imagine this is going to lie in there, kind of recess there. But if we take this as our initial box to examine, what's the volume of this box? Okay, so the volume of the ith box is delta VI, we'll call it, and it's just going to be equal to base times width times height, right, basically, right? And so we can think of it like delta XI, delta YI, delta ZI, right? That product of those three dimensions. Okay, that's going to give us the volume. Now, if we were to aggregate over all the volume of all of these delta VIs, then we would come up with an approximation of the volume of Q. Okay, and just like before, we can define a norm. Okay, the norm, which we'll call, we'll just denote in the usual way here. The norm of the partition can be the length of the longest diagonal. Okay, it can be the length of the longest diagonal of the n boxes. Right, so there's something we can define such that we know when the norm is going to 0 and when it's arbitrarily small, and it's going to be the length of this longest diagonal. And so there's some diagonal in here. Okay, and so we've got an approximation for each of the cubes. The cubes and the collection of all the cubes that form the partition are an approximation of the volume. And so what we can do is we can choose a point XI, YI, ZI in each box, and we can form a Riemann sum. Right, the Riemann sum looks like this: I equals 1 to n of f of xi, yi, zi times delta vi. Right, and then by taking the limit as the norm goes to 0, we can get the following definition of the triple integral. Okay, let's take a look at the definition. Okay. So, definition. If f is continuous over a bounded solid region Q, then the triple integral of f over Q is defined as, okay, we just kind of use this notation, 3 integrals, and times f of x, y, z dv. All right, so that's sort of the notation generally, and that's by definition what we mean there is the limit as the norm of the partition goes to 0, meaning the size of all of the cubes diminishes to 0. Then it's going to be the limit as that occurs of the sum I equals 1 to n of f of xi, yi, zi times delta vi. Okay, so obviously as the norm of the partition goes to 0, the number of cubes required to partition the space increases without bound, right? And so one thing to keep in mind is that as the cubes get smaller, the number of cubes inside of Q increases without bound, right? And so this is the idea of that we've seen from all the way back at the beginning of Calculus 2 when we introduced the integral, right? The norm goes to 0, the number of representative shapes increases without bound, and that's where the integral comes from. Right, so this is the definition of the triple integral, and this is all provided that the limit exists, of course. Okay, so provided that the limit exists. All right, so, and I know I kind of tortured that a little bit, but I want to make sure to give enough time for examples. But basically, I mean, the idea is similar to the ideas that we've seen for other types of integrals. It's just in this case, the representatives are cubes, right? Instead of squares or rectangles, as we've seen with double integrals, the representatives here are cubes. Okay. Now, many of the properties that we saw for double integrals will extend naturally to triple integrals. Let's go through a quick summary of that. Properties of the triple integral. Okay, so first of all, if you multiply the function times a constant, right? So if I've got a triple integral times c of f dv like this, and I'm just going to abbreviate some of these things. So this is a real number, this is a function of 3 variables, and this is the integral. Then you can pull the constant outside of the integral, right? As you would imagine. Plus or minus sums and differences work as expected. So if I've got two functions like so, then I can break that integral up into two separate integrals like so. And then the other one is this idea of taking the region Q and breaking it into 2 or more pieces and then just separately integrating them and then adding the result. That works for triple integrals as well. So if I have the triple integral over Q of some function f, that's equal to the triple integral of Q1 over Q1 of f plus the triple integral over Q2 of f, where Q1 and Q2 combined are equal to Q. So another way to say that would be Q1 or Q2 equals Q, and there's no overlap. Okay, so Q1 and Q2 you can think of as a partition of Q. You can break Q into 2 pieces, and this could be extended to 3 or 4 or however many pieces actually. So okay, so those are properties we saw of the double integral. They hold as well for the triple integral. Okay, and that's kind of the starting point, right? So what I want to do next, just kind of go through some examples and see some of the things, some of the interesting features of triple integrals via example. Okay. All right, and so let's do this first example. This will be kind of a, hey, let's just get used to the mechanics of this first kind of example versus, you know, trying to start with a region and figure out the bounds and everything. Let's just say we're given everything we need and we just are asked to evaluate the triple integral. Right, so we're asked to evaluate a triple integral that looks like this. We've got 0 up to 2, 0 up to x, and 0 up to x plus y. And then the function is e to the x times y plus 2z. And then the order of integration will be dz, dy, dx. Okay, so can we evaluate this? So just like we saw with double integrals, you're going to have an inner integral that is where you want to start, right? So however you set this up, the integral in the middle, in the inside is the first one. So we first go through the integrand and integrate with respect to z, holding every other variable constant. Evaluate the bounds, and then we move on to the next integral, right? The middle integral. And so that one we would evaluate the integrand with respect to y, hold everything that isn't y constant, plug in the bounds, and then that would bring us to the third and final integral, which is the integration with respect to x, which should have constant bounds. Okay. All right, so let's go ahead and do this. We can first integrate with respect to z, right? So that means you've got your 0 to 2 still, and you've got your 0 to x. And what we want to do is we want to just go through this and integrate with respect to z. Everything that isn't a z we just treat as a constant. All right, so you could see that this is e to the x, then you're going to have a y times z, and then it's plus 2z squared over 2, so I'm just going to write z squared. Okay, and then that needs to go from 0 up to x plus y, like so. All right. Okay, and so then we can evaluate this. Okay, and so everywhere you've got a z, you plug in an xy, and then subtract everywhere you've got a z plugged into 0. So it'll be e to the x, and then it's going to be y times x plus y squared. Okay, and then minus, and then it's e to the 0, and then it's 0 plus 0. dy dx. Okay, so we can simplify this a great deal before moving on, and so we'll have e to the x, and then this is xy plus y squared, and then this guy here, if you sort of expand this, you get x squared plus xy plus y squared, and then this is 1 times 0. Okay. All right, let's go ahead and combine some of these terms just to make sure that everything is cleaned up before we proceed. So I think I get, what do we get here? X squared plus 2xy plus, oh sorry, that should have been a 2, so it should be 3xy plus 2y squared. There we go. Looks good. All right, and now what we would do is we would go back through and evaluate everything with or integrate everything with respect to y. Okay, and so when we do that, we would go like so. We would have e to the x, and then this is going to be x squared times y, and then 3xy squared over 2. And then 2y cubed over 3. Okay. And that's going to go from 0 up to x, like so. Okay, you can notice with the lower limit, all of these terms will drop out, so you really just need to worry about evaluating at the upper limit. And what do you get? You get e to the x times, and then this is x squared times x, so x cubed. And then this is 3x cubed over 2. And then this is 2x cubed over 3. Okay. And, well, we can clean this all up. These can all be combined. They are like terms. They just need to have the coefficients sorted out. And so when we do that, what would we do? We'd say e to the x, and then this is going to be 6x cubed plus 9x cubed plus 4x cubed. Right, just getting the common denominator of 6 there. And so we would have 0 to 2, and then it's e to the x times, what is that, 19x cubed over 6. Okay, and so before we go into the final integral, let's go ahead and factor out that constant. And you can see that we've got x cubed e to the x dx that we need to sort out in the final integral. And this integral here, I mean, if you look at this, you can probably see that this is going to require integration by parts. Right, so this is going to be an integration by parts example. So let's go ahead and do that, and I'll just start on a fresh sheet here. So I've got 19 over 6, integral from 0 to 2 up to 0 up to 2, and then it's e to the x cubed e to the x. Okay, and so we can use integration by parts, and just in case we're rusty on this, We'll say u is equal to x cubed, du is equal to 3x squared dx. We'll set dv equal to e to the x, and that means v is equal to the integral of e to the x dx, which is e to the x. Okay, so remember the integral of, so the way this works is, so the integral of u dv is equal to u times v minus the integral of v du, right? That's kind of the setup. So you want to start by defining a u and a dv, which we have here. And then given the u, you have a du, and given the dv, you have a v, right? And then you can plug it into this form. And you kind of iterate through it until the integral settles down into something that can be evaluated. And so we can rewrite this as follows, right? So it'll be u times v, so that's x cubed times e to the x, minus the integral of v e to the x du. So that's going to be minus 3 times the integral of x squared e to the x dx. Okay, now remember, this is a definite integral, so we have to keep track of what the bounds are doing. They're coming along for the ride here, basically. But we can't evaluate the thing until we deal with the integral. And so here you can see we'll have to do another round of integration by parts to settle this piece here. Okay, so again, we'll say u is equal to x squared. That means du is 2x dx. And we'll set dv equal to e to the x. And similarly, that means v is equal to e to the x, just like above here. Okay. And so we would have 19 over 6. And then it's x cubed e to the x minus 3 times, right? Now what happens here? Well, same story. We'll say x squared e to the x minus 2 times the integral of x e to the x dx. Okay. And yet again, we'll have to use integration by parts a third time. Okay, so u is equal to x, du is dx, dv is e to the x, and v is equal to e to the x. Okay. So for this last one, this will be the last one, we get, kind of going through it here, we get x cubed e to the x minus 3x squared e to the x plus, now you have to remember to multiply these through, so you get plus 6 times, and now here's the last part you plug in, and you get x e to the x minus the integral of e to the x dx. And that's from 0 up to 2. Okay, and so now this integral we can evaluate. So let's just run through it here. 19 over 6 times x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x. Okay. So yeah, I mean, it's just a tricky integration by parts problem. But now we've got it into this form. Let's factor out the e to the x and combine terms if we can here. So let's simplify just a little bit before we try to plug everything in. So we've got the e to the x, and then I guess that's it, isn't it? Yeah. Minus 3x squared plus 6x minus 6. Oh, that's still better to look at, right? Okay. And then finally, we can just plug everything in. So we'll start with the 2. And we have e squared times 2 cubed minus 3 times 2 squared plus 6 times 2 minus 6 minus e to the 0 times 0 minus 0 plus 0 minus 6. Right, so 0, 0, 0, minus 6. E to the 0 is 1 also, so keep that in mind. Okay, and then we can finally just combine all of this, and what do we get? We get 19 over 6, and then it's what? E squared times 8 minus 12 plus 12 minus 6 minus 1 times negative 6. Okay. And what is all that worth? Well, you got 19 over 6. E squared, and this is just 2. So it'd be 2 and then plus 6. Okay. And so, I mean, that we're, at any point we could probably stop, plug this into a calculator, and get an approximation if we wanted to. But I guess maybe the best form here would be to say this is like 19, and then e squared, 2e squared over 6 would be e squared over 3 plus 6 over 6, so plus 1. Maybe this is the best way to leave it exact. Okay. And so all of this is... that's what this integral that we started with amounts to. Okay, and so again, this one was a little bit, I mean, it was straightforward for the most part algebraically. It wasn't too complicated, but it did have a, it did end up having that integration by parts section that was a little bit, I mean, you might have to review integration by parts for that piece, but all right. Now let's do an example where we have to start from a given solid, and we have to evaluate what the limits happen to be. And so let's kind of start by just talking that through a little bit. So to find the limits for a particular order of integration, it's a good idea. I mean, in general, you want to begin with the innermost limits. Okay, and the reason is probably obvious, but like if you start with the innermost limits, that needs to be a function of the outer two. Right, so you wouldn't want your second integral to be the function of the outer two. You want the most inside integral to be a function of the outer two, and as you move to the middle integral, that needs to be a function of just the outer variable, and then the final integral has to be just real valued limits. Right. So for example, given an integral like this. Right, we would want to first figure out what the bounds are for z. We want to first identify the bounds for z. Okay, which means, you've got your integral, and then you've got this inner piece here, right? And this needs to be a function of x and y. In this case, right? Z is the inner one, x and y are the outer ones. And so this needs to be a function, the bounds need to be a function of x and y. Like so. Okay. And then typically if you can identify this inner integral, then the other piece of it, the other two, they can be basically you can use the same techniques that we saw for double integrals to figure out that piece of it once you have this innermost integral identified. Okay, and what will it basically end up doing there, if you want to think about it like this, is let's say I've got my XYZ plane and I've got some shape. I'm just going to keep it simple and make like a rectangle. Right, let's say I've got a rectangle in three-dimensional split space here. There's my y, my x is down here, and my z. Okay, now this top surface, right? So the solid region is really going to fall between two surfaces. This top surface you can think of as your G2, and then your bottom surface, that's like your G1, right? And then the solid is really formed by the mashing together of those two surfaces. Okay, and then what's going to end up happening is that surface, those surfaces are going to create a projection into the XY plane. Kind of think of it as a shadow. I suppose you kind of think of it like that. But it's going to create a projection onto the XY plane. All right, and that projection onto the XY plane is what you're going to use to set up these two pieces. Okay. Right, so you first have to integrate between the two planes, the top and bottom, that form the solid, and then secondarily you consider the projection on the XY plane for your other two bounds, for your other two integrals. Okay. All right. Okay, and then that piece of it, this piece, will work like a double integral. Okay. All right, let's do an example. Let's do a concrete example, and this is a pretty relatively straightforward example. But let's find the volume of the ellipsoid given by this function. So it's 4x squared. It's this equation: 4x squared plus 4y squared plus z squared equals 16. Okay, so we got this equation here, and this describes an ellipsoid. Now I'm going to try to draw this, but you're going to have to bear with me here because it's kind of tricky. So I'll try to draw. I'm going to start with the axes, I guess. Okay, so you've got your z-axis, y-axis, x-axis. Now, what I'm going to actually do is I'm going to cut a cross-section out of this first, and just kind of bear with me. This will hopefully all come clear in a second here. So I'm cutting a cross-section, not a cross-section, I'm going to cut a quarter out of this. Okay, and the actual shape kind of does one of these. It's basically symmetrical above and below the x-axis, or the xy plane. It's symmetrical. Just looks kind of like kind of think of it like this. It's a little more oblong than that, but right, kind of has a right, so it's like cylindrical, kind of cylindrical here, and it doesn't have like, it doesn't bulge out like that. It's just bad drawing. But what I've done here is I've cut out this one 1/8 section of it, right? So basically this is the positive. This is quadrant 1 of the XY plane. Then there's quadrant 2, quadrant 3, quadrant 4, right? So for each quadrant, you've got an above and a below portion. And so basically there's 8, you can kind of think of it as 8 octants. So there's 8 octants to this ellipsoid. And I'm just looking at the first one. Okay. So you can think of in here, you've got maybe 1 and 2 on the y-axis, and we'll say 1 and 2 on the x-axis. Right, and then this would be -1, -2 on the x-axis, -1, -2 on the y-axis. You know, and then it extends, has some height, but it's perfectly symmetrical about the origin here in the z direction. Okay, and so for this figure, given the fact that it's symmetrical, we can simplify the calculation by basically considering just the portion of the ellipsoid that's lying in the first octant, right? So just this section up here. So we can simplify by considering just the figure, well, only the portion in the first octant. Okay, and so then basically whatever we come up with for bounds there, we run the integral and then we multiply times 8 to get the volume of the whole figure. Okay, so just kind of starting with, we'll just assume that, you know, we're going to go with a dz, dy, dx order. So we'll start by trying to identify the bounds on z. And this can be done by just looking at the expression and solving for z, right? And if we do that, the bounds on z, are, well, z is going to vary between, you can see 0, for this octant, it's going to be between 0 and then whatever this line is here. So 0 and then whatever this line is. And it turns out that line is given by z equals 2 times the square root of 4 minus x squared minus y squared. So this would be the lower bound, the upper bound for the inner integral. And this isn't pretty, but I think it works out in the main for this. It's not too bad. And then if we just look at what's happening in, so if you think of the solid as being above the upper portion, then what we're looking at down here is the cross section, the so-called projection into the xy plane. And so that we can say, well, let's make, since x is the outside piece, then x is going to go from 0 up to 2. So that's the outer integral. And then that inner integral is going to be, so y is going to go from 0 up to whatever this line is here. And we can figure out what that line is. It's basically a circle, isn't it? You've got a circle in the xy plane, essentially. Right? And it's just, you know, the circle could be considered, it's x squared plus y squared equals 4, right? Because it's centered at 0 and the radius is 2. So that means the bounds on y must be 0 less than or equal to y less than or equal to 2 times the square root of 4 minus x squared. Right? And that can be got to just by thinking of this as a circle, and this is just a quarter slice of a circle. Okay. Okay, and so we can use this information to set up the triple integral. Okay, and so the triple integral in this case is just going to be, we'll just write it out first. Like this, that calculation there can be got at, remember to multiply by 8, since we've broken into 3 parts. The outer bound goes from 0 up to 2. And then the middle is 0 up to 4 minus x squared square root. And then the inside one goes from 0 up to 2 times the square root of 4 minus x squared minus y squared. Okay, and then it's dz, dy, dx. Okay. And it's relatively straightforward to do this. So we can do the first one, start with the inner integral naturally. And we have this, and then it's just z, isn't it? Z, and then you have to evaluate it from 0 up to this. This 2 times the square root of 4 minus x squared minus y squared. Right, and you get 8 times 0, the integral from 0 to 2, and the integral from 4 minus x squared square root. And then the bounds, obviously, you just plug in the expression. Like so. Okay. And then we can go to the next page here. And this guy we can evaluate. Now it turns out, actually, this one is, so let me rewrite it here so we can look at it. right, so it looks like this. So it turns out this one is pretty darn tricky. And so what we want to do here is we want to use an integration table. A lot of the integrals that you will run into in the final sections of a Calculus 3 course, they can get pretty hairy. So integration tables don't have a large place in calculus, but they do when the integrals get too nasty, right? When the point of the problem isn't calculating the integral, it's more like setting it up. So in this case, perfectly legitimate to go in and look this guy up in a table. And when you do that, you'll see, oh yeah, I'm glad I did, right? So when I integrate with respect to y here, I'm going to get y times the square root of 4 minus x squared minus y squared plus 4 minus x squared times the arc sine of y over the square root of 4 minus x squared, right? That's the argument for the arc sine here. Okay, and then that's going to go from 0 up to 4 minus x squared square root. Okay, all right, so that's pretty awful. But it turns out this thing simplifies down a ton when you plug this bound in, right? And so in particular, everywhere you see a y, you're going to plug this in. And so notice this term here. When I plug in square root of 4 minus x squared for this, and I square it, then I get 4 minus x squared minus 4 minus x squared. So this whole radical here goes to 0, right? So this whole thing is just 0, which is great, because that was starting to look awful. Now this piece here, I get 4 minus x squared, and what happens when I plug in square root of 4 minus x squared for y here? I just get arc sine of 1. Right, so what I end up with here is plus 4 minus x squared times the arc sine of 1. Okay, and then I've got to subtract the other side. And when I plug in zeros, I get a 0 here. So that'll be 0 plus 4 minus x squared. And then this will be arc sine of 0. All right. And what do we get? Simplify this down. Arc sine of 1 is pi over 2, right? So the sine is equal to 1 at pi over 2. The inverse sine is only defined from 0 to pi over 2, or 0 to pi, and so that's the only place in that interval where we have sine equal to 1 is at pi over 2. So you should get here, you'll get 4 minus x squared times pi over 2. That's this piece coming down here. And what happens over here? Well, arc sine of 0, where does sine equal 0 between on the interval where the arc sine is defined? Well, it equals 0 at 0 at 0 degrees, right? So this whole thing is just zeroed out, and you just have this nice simple integral here. Okay, and this one is very easy to integrate, but let's first let's just write this as 8 pi over 2 times the integral from 0 to 2 of 4 minus x squared dx. Okay, and so when we integrate here, we get 4x minus x cubed over 3, and then that needs to run from 0 to 2. And so what do we get? 8 pi over 2 times, so that'll be 8 minus 8/3. And then when we plug in the 0 at the bottom, you get 0 minus 0. Okay, so it's 8 pi over 2 times 24 minus 8 over 3. So 8 pi over 2 minus 16, or times 16 over 3. All right, all in here you get 64 pi over 3. Okay, so that's the area. This is the area of this shape we drew at the onset, this giant ellipsoid. right? That where we cut out a cross section of it here, right? And we figured out what the bounds are on that cross section, or this eighth of a section of the entire shape. I should stop saying cross section. We cut out this eighth of a section, figured out what the bounds are, set up the integral for just that 1/8 of the piece, multiplied the whole integral by 8 because there's 8 such sections in this thing, and the result is 64 pi over 3. Okay. All right. Very good. So in this example, and we didn't set it up differently to verify this, but it turns out, well, if you do set this up with different integration order, like maybe instead of dz dy dx you do dy dx dz, for example. If you set it up differently, you'll get the same answer. And in this case, the order in which you evaluate the integrals, it doesn't make a big difference in terms of complexity. Right here, we had to go to an integration table. Pretty much any order you use, you're going to have to probably resort to an integration table because the integrals get pretty messy otherwise. But it is the case that you may come across triple integrals where one order of integration is much preferred to another. Okay, and so the example I want to run next, which will really be the last example, is an example where setting up the integral in one way leads to almost an intractable problem, and setting up an integral in a slightly different way leads to a relatively easy time of it. Right? So let's take a look at this last example here. I have to go flip this. Okay. Let's look at this last example. So we want to evaluate a triple integral that looks like this. So you've got 0, and then this will be pi over 2, the square root of pi over 2, and then x up to pi over 2 square root, and 1 up to 3. And this will be sine of y cubed. And the order that these bounds correspond to is dz, dy, dx, sort of the natural order. Now, if we integrate with z first, as indicated, followed by y, then what we'll end up with here, after we do the first integral, is we'll end up with the following. We'll end up, so if we start with z, we end up with a middle integral that looks like this: 2 times integral of sine of y squared dy. Now, sine of y squared dy is not a straightforward integral to calculate. And so if, on the other hand, if we kind of switch the order of integration around, yes, we do have to reconsider the bounds, but it turns out this integral can be made very straightforward and easy. So in particular, if we change the order to dz dx dy, the problem is much easier. Okay. Now, when we change the order of the integration, we have to rethink. How we do this, right? Because up here, x needs to be evaluated. It has to have constant upper and lower bounds. But if it's here, the bounds has to be a function of y. It can still be constant potentially, but it has to potentially be a function of y. So you have to rethink things here. dz stays the same, but these other two we have to resort out. So let's draw a picture of what this function looks like. And we'll start with the z-axis this time. So we'll go 1, 2, 3. Now this guy's kind of easy to draw, but it's also doesn't, well, we'll just draw it quick. It's not necessarily going to be perfect. I'm sure you can understand that. Kind of looks like this. Okay, so it's like it's kind of got this triangular appearance, right? It's sort of like a prism, right? Sort of like a prism, and kind of imagine it looking a bit like this guy here in space. Right, so it's a prism. Okay. And so then if I draw my y-axis here, so this is the z-axis, and I draw my x-axis down here, then the shadow or the projection looks a bit like this in the xy plane. Okay. Okay, and so a couple of points of interest, like this point here. What point is that? That is pi over 2, the square root of pi over 2. That's the z-coordinate, and then it's the square root of pi over 2. Sorry, the x-coordinate and the y-coordinate are both square root of pi over 2, and z is 3. Right, you can see z. So this is like a flat top surface. This is actually technically up here. It's in space, right? So it's like tilted forward. Okay, and then down here is the same thing, except the z-coordinate is 1 there, right? So it's down here at the bottom of the figure. Okay, and so that means these shapes here, these points here in the xy plane are both pi over 2. Okay, and this line here, what is this line here? That line is just y equals x, right? It's the identity function in the xy plane. Okay, and so kind of using this picture, we can deduce what all of the pieces need to be, right? So z is going to vary from 1 up to 3, right? So 1 is less than or equal to z, less than or equal to 3. What about x? Well, x is just going to vary from, so it starts here at the y, well, x equals 0, and it's going to come out to this point, square root of pi over 2. Okay, and then what about y? Well, y is going to vary from, let's see, hold on one sec. Yeah, sorry. So y is going to go in this direction, right? From down here to up here, right? And that is going to go from, remember, these are both at the same height on the y-axis. So it's going to go from this function here, x, up to square root of pi over 2. Pi over 2 square root. Okay, so using these three, we can set up the integral. All right, so let's do that. So the triple integral over q dv will be equal to, I'm just going to write it down here. So the inside would be 1 up to 3, that's the z, and then x will be 0 up to y, and then 0 up to pi over 2 square root. Okay, and then it's sine of y squared, and it's dz, dx, dy. Okay. Okay. All right. So let's just do this on a separate sheet of paper, in fact. I'll rewrite the whole thing here. Okay, so I've got the triple integral of sine of y squared dz, dx, dy. And it's 1 to 3, 0 to y, and 0 to pi over 2 square root. Okay, so integrating first with z, right? The way this is nice because this is all just a constant as far as z is concerned, right? So first one is straightforward. you get z times the sine of y squared, and we have to evaluate that from 1 up to 3. Okay. Right, like so. And then 0 up to y. Right, and so here you would get 3 sine of y squared minus 1 sine of y squared. So you really get 2 sine of y squared, don't you? And so I'm going to write that as 2 sine of y squared. Yeah, just write it like that. Okay, and now we have to integrate with respect to x. Okay, and again, the whole entire integrand is just a constant when we talk about integrating with respect to x, and so we get this nice situation where we have 2x sine of y squared, and that needs to go from 0 up to y dy. Okay, and so this becomes 2y sine of y squared at the top, and then at the bottom it's 0, isn't it? 2 times 0, right? So the integral is, and we can write it like this. We can pull the 2 out, and this will just be y sine of y squared dy. Now, previously, kind of on the onset of this problem, we said, oh no, sine of y squared, we don't know how to deal with that. But we do know how to deal with y sine of y squared, don't we? We just use a basic u substitution here. So if we let u equal y squared, then du equals 2y dy. And so that means we have du over 2 equals y dy. Right, and so this whole thing can be rewritten as sine of u over 2 du. Right, and so this is just going to be equal to negative cos u from 0 up to pi over 2 square root. Okay, and obviously we can't plug the pi over 2 into the u. We have to convert this back to a function of y. And so I get negative cos y squared from 0 up to pi over 2 square root. Right, and then I can evaluate this. This is just negative cosine of square root of pi over 2 squared minus negative cosine of 0. Right? Okay, and so what do I get here? I get 0 minus negative 0. This is 0 minus, and then it's negative, and cosine of 0 is 1, so I just get 1. Okay, so the answer to our last example from Calculus 3 is, interestingly enough, the number 1. Right, and so as you could see, that integration was straightforward, very easy, right? Whereas if we had tried to do it the other way, it would have been probably very difficult, or if not impossible. Okay, and so I think this will be it for Calculus 3. This will be the last section. Now, a lot of calc courses that you might take in college, their endpoints will vary. I know when I took Calculus 3 in college, we ended pretty much at this point. We introduced triple integrals, and we were expected to do a couple of them, maybe set one up, maybe evaluate a handful of them that were already set up. And so that's what we've gotten to here. Now, I really do think in most textbook you could probably make the case that there's a Calculus 4 worth of material left over. So maybe in a future lecture we'll do something like that where we pick up where Calc 3 left off and take off, kind of fill in all of the remaining stuff, but not in this section. We're not going to do it. So that takes care of Calculus 3. So we started with what is a vector, and we ended with triple integrals. So a lot of material covered over the past 20-some lectures, 25 lectures-ish. So I hope you enjoyed it, and keep coming back to the channel. We'll just keep moving through undergraduate coursework. The goal is to basically do every undergraduate course if people are finding any value at all. I think it's fun to do it, so we'll just keep going with it. So, all right, take care. Thanks for watching the series if you've watched the whole series, and we'll talk to you all later. Take care.